So you probably noticed in most of my videos, I explain how to control a ton of digital outputs using just a few pins off your microcontroller. Well, in this video, I'm going to explain how to use those same techniques to control digital inputs to the microcontroller. Okay, so before I go any further though, I just want to explain something, because I bet some of you are already thinking, I already know how to control a bunch of digital inputs to the microcontroller using just one pin, an analog input pin. And this is a pretty good technique, and I just want to talk about it real quick here. So this is the technique where you tie a bunch of push buttons all together on one side and then to ground through some resistor value. And then on the other side of that push button, you pull it up with a different value resistor, so that when you push it in, you create a voltage divider at this point, and then simply do an analog read of that. And since they're all different resistor values, there'll be a different value voltage there. So you can determine then which push button was pushed. But you know, this is good for maybe 3 or 4 push buttons, maybe 5, I don't know. But what about, I don't know, 50 or 100, or what about 1,000 push buttons? That's where this technique comes in. So let me explain what we have over here. So there's nothing really too special or fancy going on with this circuit. It's simply 2 shift registers wired in series, and one shift register controls 8 LED outputs, and then the other controls the 8 push button inputs. Okay, and they're really responsive. So they're not wired directly to the LEDs. They're actually read in by the microcontroller, and then it decides whether or not to turn the LED on or off. Okay, you can do anything you want with the push button value once you get it into the microcontroller. So I'm actually mixing inputs and outputs together in this circuit using still only 4 pins off the microcontroller. So, and it's really responsive. In fact, you can push 2 at the same time, or maybe 4 at the same time. So you can do a lot of cool stuff, which is another problem with the analog type circuit. You know, if you think about it, what if you do push more than 1 at the same time? You got to consider all those combinations read in here. So there's some flaws in that circuit. There's even some flaws here, and we'll talk about that more in a second. But let's drag out the whiteboard and really take a closer look at what we got going on here. All right, just before we get started, I want to quickly mention that I will not be getting into the nitty-gritty details about how shift registers work. Okay, so just in case you don't understand how shift registers work, check out the links in the description below before watching this video, because I'm going to assume that you already know how shift registers work, what they do, and how they're wired, and all that good stuff. So check those out before watching this video. But anyway, what we have here are the 8 push buttons I just demonstrated for you in the circuit. But what we do is we connect all of them together on one side. Okay, so right now I'm showing you 8 push buttons, but this could be 100, this could be 1,000, you know, it could be as many as you want. But you wire one side of them all together, okay? And then that will come down to the microcontroller, where you pull it down with a resistor to ground. Okay, and I'm using a 10K ohm resistor for this. And this is a digital input on your microcontroller, and it should be an interrupt capable pin, meaning that as soon as this pin goes high, because we're gonna call the interrupt on a rising edge of this pin, as soon as it goes high, or when it gets 5 volts on it, it's going to call what they call an interrupt service routine. Okay, it's a chunk of code that will be executed as soon as this goes high. So wherever you're at in your normal program, if this goes high, it's going to yank you out and execute that code. Okay, kind of basic stuff. And once we look at the code, that'll make more sense. But what we have here though, okay, one side all connected together. On the other side here, these go to the shift register outputs. Okay, so this is your QA or Q0 all the way through, okay? And they connect directly into these push buttons, okay? And on boot up, when we start our program, what we'll do is we'll make all of the outputs high. So we'll shift out a byte to this shift register with a value of 255. So all 8 bits will be high, okay? And what happens then is, you know, we're going through our program, whatever, and as soon as one of these push buttons gets pressed, we'll get current flow through this, and it'll pull this pin high, okay? And it'll call that interrupt service routine, that routine that executes code. But see, the problem with this though is that you don't know which push button was pushed. So as soon as that code is called, what we do then is, instead of making them all high over there, what we'll do is we'll make just one high. 0, 0, 0, 0, 0, 0, 0. So we'll write that to the shift register almost immediately. So that what we're trying to figure out now is which push button was actually pushed. So if it was indeed this one, and we write a 1 to it, then and this is still high, that means current is still flowing there, then that means that that push button was the one that was pressed, okay? And if it was not pushed, or it doesn't matter if it detected if it was pushed or not pushed, because it'll do this anyways. It'll then simply shift that bit over and then write that to the shift register. Okay, so it'll shift the only one pin that was on over one, and then check this. Is this pin still high? If it's not, then that pin was not pushed. Okay, and the reason I'm talking about shifting it all the way through before just giving up when it does find it is because if you push more than one push button. So, you know, if I'm pushing this one and say this one, then eventually it'll get down there. And I mean, this happens so fast, so that if I did push both of these, it would eventually also register that one. It would know that you also pushed that push button. Okay, so that's how it works. I mean, it's as simple as that. There's really nothing more to it. And I just wanted to talk about the technique here on how to do this. Okay, so if you had, say, another shift register over here, then you'd have to write in your code, you know, that you're gonna shift the 1 all the way through the first shift register, and then make that one chill out for another 8 cycles while you shift the 1 through the next shift register. Hopefully that's making sense. You know, as always, I don't ever really plan these videos out, so I kind of just think about what I'm going to say as I go. So there is one problem with this circuit, and some of you might have already noticed what the problem is. If you do push 2 at the same time, that could be really bad for your shift register. Think about it. As you're shifting a 1 through this, and I don't even know why I just erased those, but as you're shifting a 1 through these, this pin right here is 5 volts off the shift register. This is 0 volts. So if I push these 2 at the same time, that's a dead short into the shift register, because right now when this is 5 volts, this is sourcing current, and when this is 0 volts, it's sinking current. So that's a dead short to ground through there. So you got to do something about it. In fact, if you did do that, this guy over here would detect nothing. It would stay at 0. This would sink all that current. So what you got to do, and by the way, these shift registers may be protected, so you may not blow them up, and they may have their own version of what I'm going to show you here. So what you got to do on each push button is either put a resistor on each one. And these are basically just current limiting resistors. So you can make them all like 1K, 1K. You don't want to make them too big, because then when that goes high to 5 volts, you're creating a voltage divider here with the 10K down here. So that's one way to do it. And if I push both of these in, I won't damage anything, but I also would not register either of them as well. Okay, because this is still 0. So then I would actually get like 2.5, and then you also have to figure out what you got going on here with the 10K over here. So anyways, that's one method, but that's still not the best. This is what I did. I used diodes, and I'll explain why here in a second. I don't have to write all of these in, but I use diodes because we don't really care about sinking current into the shift register. So when we have 5 volts in 0, 0, and we push 2 at the same time, this 5 volts here will be, this diode here will be forward biased, okay? 5 volts on this side through 10K to ground, right? So this pin will go high. It'll actually be somewhere around like 4.3 volts, okay? Because there's a drop with the diode. But this will not conduct because I'll have 5 volts here. So when I do push both at the same time, this diode here is reverse biased, so it will not conduct. And I don't know if you guys are familiar with diodes or not, but they only conduct current in one direction when they are forward biased. So think of them as, you know, they need to be high on one side with respect to the other side in order to conduct. So if I have 5 volts on this side and a lower voltage on this side, it will conduct and I'll get my voltage across there. Okay, hopefully that makes some sense. But what this allows you to do then is push 2 buttons at once. So if I sat here and held these 2 buttons together, right, I'll register this one first because it'll go 5 volt 0 0 0 0, you know, and then it'll shift the bit over, and then this one's now 5 volts 0 and 0. So now that one can conduct at 5 volts, and these will not conduct, those diodes. So I'm protecting the outputs of the shift register, and basically that is what I have right here. I doubt you can see on the camera all of the diodes that I have there, but that allows me to push 2 at the same time and register those. Okay, so I mean, that's pretty much it. That's the technique. So now we can jump over into the code and really sort of get a firmer grasp of what's happening here. All right, so here's the code. Nothing too special here, and as always, I kind of just wrote this in a very rough manner just to get it up and running and to debug the whole thing. But it does work, and it works pretty good, so it might work for you guys. But you know, there's no comments or anything in here explaining how anything works, so we'll have to go through it line by line here. And of course, it will be available on my website, link in the description. So what we do first is include the SPI library, and we'll talk about that here in a second. Then we do some variables, jump into the void setup, and since we're using the SPI library, we have to use these dedicated pins for that. So we've got your data and your clock. You know, pin 13 is your MOSI pin, master out, slave in. Pin 11 is your S clock, okay, and you have to use these for the SPI library. And the reason we're using SPI, not just shift out, is because it is so fast. Okay, you can actually run this, and we'll talk about that in a second here. But then also we have pin mode 4, and we'll set that as an output. So here's your 3 pins you need for the shift registers. Okay, data, clock, and latch. The latch pin could be any pin you want. Okay, so pin mode 2 is your input from the push button. So on the one side of all the push buttons, that feeds into this pin. Okay. And then we'll go ahead and set up the SPI library, most significant bit first, and the mode is 0, and then the speed is SPI clock divided by 2. So this thing's going to run at 8 megahertz, so that's ridiculously fast, and that's why I use the SPI library for this. And then we'll go ahead and kick it off, spi.begin. Okay, so what we'll do first now is shift some data out, and we only have 2 shift registers, so we only have to shift out 2 bytes at a time. So what we'll do is send out a 255. Okay, so that's 8 ones. Okay, 8 bits all with a value of 1. Okay, and the way we have these shift registers wired up is the data pin is going to the LED output shift register first. So when we shift this in, it goes into the first shift register, but followed up, we send all zeros. We send 8 zeros. So what that does is it shifts all these ones over to the second shift register, which is controlling the push buttons, and then we get all zeros for the outputs, the LED outputs. Okay, then we latch it. 4 high, 4 low. Done. That's how easy it is to control shift registers. It's ridiculous. Okay, and yeah, I set up the serial here just in case I needed it. I don't think I used it anywhere though. And then we'll attach the interrupt. So interrupt 0 pin read is the function we'll call, and it's on the rising edge of that pin. Okay, so digital pin 2 is interrupt 0. Here's the void loop. Nothing there. Okay, nothing occurs in the loop. This is all happening in the background. So as soon as that pin goes high, bam, calls this routine here, and it jumps in, and you'll notice a little bit of a kind of weird thing in here. So we do a for loop right away, 50 times of 1,000 microseconds. So that'll give us 50 milliseconds, And the reason I didn't just go delay 50 is because the delay function doesn't work in here. Okay, that's one of those gotchas. So you have to use the delay microseconds in here. I guess the delay function actually uses interrupt, so that's kind of why it doesn't really work in here. So anyways, the reason we have a delay though in here at all is in case you do push. It's like a debouncing. So right when you push the button in, it might go fly up and down a little bit. So we want to make sure it's solid on before we actually check anything. Okay, so this is called, and it does it 50 milliseconds, but this also checks or allows, in case you push two buttons at the same time, it's kind of allows both of them to be pushed in. Because you know when you push two buttons in, it's not like you're pushing them in at the exact same time. So you're giving it 50 milliseconds for that to happen. This value check here is equal to 1. We'll talk about that more in a second. And then we jump into this little loop here that happens 8 times. And this is how we go through and check each of the push buttons. So remember, right before this, we have all 1s on the push button. So we don't know which one it is. So now we're going to find out which one it is. Okay. So we'll do an SPI transfer of check and then output. Okay. Remember, this one, whenever we write to it first, this is actually going to the push buttons. And then it goes to the LED outputs. So we have a byte here called output, and this is to update the LEDs. This check here, is going to the push buttons, and we're only sending over a 1 first. So we sent over a 1, and then we'll latch it, and then we're going to hang out for 500 microseconds just to make sure that the pins all go high, okay? And then we'll check it. If now the push button pin, digital pin read 2, went high, and then we do let's just say it did go high. If the bit read of output of J, so we're at 0 now, is equal to 1, then bit write J 0. So what we're doing here is just checking the pin. What was it last written to? Okay, because output is the byte that we're going to send to the LEDs. So we're just checking to see if it was already a 1. If it was a 1, make it a 0. And if it was not a 1, make it a 1. Okay, that's all this is doing. Okay, I know it's probably a stupid caveman way of doing it, but that's all it is. Okay. So we're just checking it, flipping the LED, all right, and then you're done. Then, okay, so what you'll do next is you'll shift the 1 that was here, because right now check is just a 1. It's 7 zeros with a 1 in it. So all 7 zeros with a 1, and then when we shift everything over to the left once, it'll shift this 1 that we had here over to the next spot over, okay? And then it'll continue this for loop. So now the 1 is in the second position over, and it'll check it again. And that's how it works. It goes through it 8 times, each bit in the byte until it's done. And then finally, once it's checked it and it's found which pin went high, it will then send out all to the push buttons, all 1s. Okay, so it'll resume its last state. So now everybody's at 1. So anybody could trigger this to the interrupt here. And then we'll update the outputs with the actual output byte. Well, we were kind of doing that here as well. So we'll send over that byte, latch it in, and then what we do here, this is kind of interesting. So what we do here is we wait for your finger to let go of the push button. So if you pushed it, it'll go through all this, but my finger's still on the button. We don't want to jump out of this because the LED will just flicker. It'll keep calling this thing. So what we're doing here is just waiting for you to let go. So this is a infinite while loop while you're still reading that pin is high, okay? And it's just doing nothing in here. It's waiting for you to let go of the button. Okay, and then that's it. That's the whole thing. So I kind of rushed through this, but I hope that sort of it makes some sense. And you know, obviously this code is written horribly, and you can improve upon it. But that's not what the point of this video is. I'm really trying to just drive home the technique in controlling a ton of inputs here. Okay, so that's the video. Thanks for watching.